In this video, we are going to derive the limit, okay, so the limit as x approaches 0 of the sine of x over x. This is what we're going to derive today, this limit. Now, this limit is actually really important, and the reason why it's so important is because it's actually used in figuring out the derivatives of sine x and cosine of x. That's the reason why this limit is so important. And so in this video, what we're going to do is we're going to actually figure out what this limit is. But how do we do that? To be honest, this limit is actually a really difficult limit to figure out, like on the first try, like without any knowledge of what it is or anything, right? It's pretty difficult to figure out. And it turns out what we could do is we could actually use the squeeze theorem to figure this out. And pretty much what we're going to do is, in order to use the squeeze theorem, well, before we get to that, we're going to think of x right here as an angle. Because when we take the sine of x, it's like we're taking the sine of an angle, right? And we're going to represent this angle on a unit circle, right? Kind of like how sine of x works, comes from the unit circle. So we're going to just do that, right? And I'm going to draw that right here. So right here. So I'm going to draw a part of the unit circle right here. Right, so this right here, just a part of the unit circle. And I'm going to say that our angle is something like this. Right, so this right here, we'll just say that this is our angle x. Right, intercepts right there. So this is pretty much what we have. And since it's a unit circle, that means that the radius of our circle is 1, and the radius right here would have to be 1 as well. Now, it turns out, like, to figure out this limit, it doesn't matter what we call the radius. It's just calling it 1 would be it makes it simple, right? So, again, as I said before, what I said was we're going to use the squeeze theorem to figure out this limit. But how? How are we going to use the squeeze theorem to figure out this limit? What are we going to do? Well, we're going to pretty much apply the squeeze theorem to this diagram that we've drawn here of our circle, and pretty much we're going to use the squeeze theorem. And the way that we're going to use the squeeze theorem for this diagram is we're going to divide it up into different areas, and we're going to use areas as the basis for how we use the squeeze theorem to derive this limit. So how could we divide this sort of figure up into areas? Well, we could make a triangle right here by connecting this point to that point right there. So we have a triangle, as you can see. And here's another thing we could do, okay? Just go with me, okay? I'm going to draw a tangent line right here to construct another area. So if I do this, I'm going to construct a tangent line to the circle such that if I were to then extend this line right here, all right, and extend that line, it will intersect at a point between that and the tangent, or it will intercept at that point, forming another triangle. As you see, we have a large triangle there. In fact, this triangle right here should be a right triangle because we have a tangent line right here intersecting with a radius at the point of tangency. So that means that this would have to be a right angle, and so this is a right triangle. Now, how do we we divide this up into areas, and notice the areas that we have here. Okay, we pretty much have, I'm going to call this area 1. So I'll call this A1. And this area right here, I'm going to label it like this. Right, that area right here, this thin area right there, I'm going to call that A2. Okay? And then the rest of this area right here, I'll call that A3. All right, so we have 3 areas we've divided this up into. Right? So the way that we can use the squeeze theorem is, here's how we could do it. Okay, I'm going to write it right here. So the way we could use the squeeze theorem is we could say that A1, right, that's area 1. I'm going to write it slightly larger because we'll have space. Right? A1 is less than or equal to A1 plus A2, which is less than or equal to A1 plus A2 plus A3, right? So A1 less than or equal to A1 plus A2, less than or equal to A1 plus A2 plus A3. And it turns out that this idea, this is always true no matter what x is, right? No matter what x is, right? A1 is less than or equal to so A1, this triangle, is always less than or equal to A1 plus A2, right? This sector right here, which is always less than or equal to A1 plus A2 plus A3, right? This large triangle. That's always true no matter what x is. And that's an important idea for the squeeze theorem. I mean, if we have, let's remember what the squeeze theorem is all about. It's pretty much we have something like that. Let's say we have that and this. So an important part of the squeeze theorem is that one function is always above this middle function right here, and the other function is always below that middle function, right? And so that's a very important idea of the squeeze theorem. But there's another part to the squeeze theorem we have to consider. It's the fact that not only is this one always above, this one always below, but they become really close to each other at the point that we're investigating, which in this case is x equals 0. So notice how when x approaches 0, right, the angle becomes really small. What happens is area 1 approaches 0, area 1 plus area 2 is going to approach 0, it's going to become really small, and area 1 plus area 2 plus area 3 is also going to approach 0. So all of these areas are going to approach 0. They're going to approach that same point. And so, as you can see, the squeeze theorem would be valid. Now, just because these areas approach 0, that doesn't mean that this will approach 0. We haven't even brought sine x over x into the picture yet, so it has nothing to do with that. We're going to, though. Okay? So how we do that, I'm going to show you. But anyways, that's the idea that we're going to use. Now, that we know that, we have to actually find what these areas are in terms of x. And to do that, we got to pretty much figure out what some of these lengths would be. And find those lengths, pretty much, we should just find some things. We already know that this is 1, that's 1. But remember, we got to find areas of triangles, the area of this sector, which can be pretty easily done. But you have to find the areas of the triangles, right? So as for the area of this triangle, we have the base and the height. Well, the height, I'm just going to represent like this dashed line. And this is a unit circle. So, and by the way, since this is the height, that'll be a right angle. Since this is a unit circle, and this is where we intercept, we know that the coordinate of this point is going to be cosine of x comma sine of x. Technically, you should say theta, because normally this would be the x direction, and this would be the y direction, right? But in this case, we're representing as x. So it's just going to be the cosine of x sine x. So the x coordinate right here, this would be the cosine of x, right? This length right here, cosine of x, and this height, sine x. We know about that idea from the unit circle, right? So cosine x, sine x. And another length that we should figure out before we find these areas is we should probably find this length right here. How do we find this length? Here's how. Notice how we have two similar triangles here. This right triangle right here is similar to this larger right triangle by angle-angle similarity. And the reason why is because they both share this angle x. They both share that angle, and they both have two corresponding right angles. We know right angles are congruent. And as a result, they're similar by angle-angle similarity, right? So that means that these triangles, they're similar. And because those triangles are similar, that means their side lengths are proportional to each other. So we could say that the ratio of this side length to that side length has to equal the ratio of this side length to that side length. So pretty much this length divided by this length is equal to this length divided by this length. So this is our unknown, right? Pretty much this length over this length is sine x over the cosine of x. That's equal to that unknown length that we don't know. So it's equal to that divided by this whole length, which is 1. And anything divided by 1 is, of course, that same thing. And so you can see how this unknown length is just the sine of x over the cosine of x, which we know is equivalent to the tan of x. So it turns out that this length right here is the tangent of x. So we're just going to rewrite this as the tangent of x. Right? that's pretty much it. And it's interesting because it's tangent to the circle, so that's probably where it comes from. Right? That's the whole idea of that. So now that we have figured out all these lengths, we're ready to find each of these areas. So the first thing to find is area 1. So to find area 1, it's a triangle. Pretty much area 1 refers to this whole triangle right here. We know it's going to be 1/2. So pretty much area 1 is going to be 1/2 the base of the triangle times the height of the triangle. So the base is 1. So it's going to be 1/2 times the base, which is 1, times the height, which is the sine of x. So as a result, A1 is equal to the sine of x over 2. That's it. So we're going to replace A1 right here with the sine of x over 2. So that right there, A1 is there. I'm going to move this over to the slightly to the side because it'll help. So A1 is sine of x over 2. Next, we have to find A1 plus A2. All right, we got to find A1 plus A2. So I'm just going to erase a little bit of this stuff. So now we're going to find A1 plus A2. And to find A1 plus A2, actually I shouldn't really erase that, but that doesn't really matter. A1 plus A2 is the area of a sector. It's this sector right there. So as you can see, it goes along that arc. And we know how to find the area of a sector. It's pretty much just a fraction of the area of the full unit circle. And that fraction refers to our angle, which is x, over the full 2 pi radians, times the full area of the circle, which would be pi times the radius squared, or pi times the radius of the unit circle, which is just 1 squared. And so this would be it, right? That would be the area of our sector, right? In the area of the sector, right? Notice how 1 is just 1, so we can just write that as 1, right? That's pretty much it. But notice how pi cancels out, and we're left with x over 2. So this is A1 plus A2. Pretty cool, right? I don't know how I did that, but I would not be surprised if that was not the first time I did that. Anyways, x over 2 should be less than or equal to, right? So we found A1, we found A1 plus A2. The last part we need to find is A1 plus A2 plus A3. And I'm not going to erase this until slightly later because we can fit all this. To find A1 plus A2 plus A3, I'm not erasing. This is just a triangle, right? It's a triangle, so we're going to do 1/2 base times height. So 1/2 the base, which is just a length of 1, times the height, which is tangent of x, right? And so we can write that as the tangent of x over 2. So for our last piece, tangent of x over 2. And since we're building down this way, I think it's appropriate to erase now. There we go. So now that we have this, hopefully we have enough room, there's one thing that we need to do to this. It turns out that we have to put absolute value signs here. The reason why is because areas are positive, right? When you want to calculate the area of something, you're always going to get a positive result because it's length times length. It's always going to be positive. And so that's the reason why. And some of you guys may have arguments for that. And so I'm going to actually show you why we need these absolute values here. But before we do that, notice how these 2's, they cancel out. And so we could just write this as the sine of x is less than or equal to, x is less than or equal to the tangent of x. So now that we know this, why do we need these absolute values here? Well, let me show you why. Let's just assume that those absolute values aren't there. We're just graphing each of these functions without their absolute values. Well, going over here, if we were to graph x, then this is it. That's x. That's y equals x. Now, if we were to graph the sine of x, it's going to look something like this. based on the squeeze theorem, it kind of makes sense that's going to kind of approach 0 like that. And so, yeah, that makes sense. And also, it's going to do something like this on the negative side. And notice what happens. Notice how on the right side of 0, sine of x is less than x. But on the left side of 0, sine of x is greater than x. That makes it invalid to use the squeeze theorem, because sine of x would have to always remain below x for the positive side and the negative side within the vicinity of this point that we're focused on. So, as you can see, we need the absolute values there, right? So this would be the sine of x. We need the absolute values there, or else the squeeze theorem won't work. And so we need to make this the absolute value of x. And so let me show you what happens when we use the absolute value versions of these. We already know what the absolute value of x is going to look like. It's pretty much doesn't have this negative side. It's going to pretty much extend like this, and that would be the absolute value of x. It extends in that direction as well. So I'm just going to label it there so we can see. And for the absolute value of sine of x, pretty much whenever you take the absolute value of a function, it takes all the negative parts of the function and makes it positive. So pretty much what that means is this negative part right here is just flipped around like that, which becomes positive. And right here, it would also become positive, and right here it would become positive. So you can pretty much see the whole idea of that. And yeah, there we go. So this right here, sine of x. And I didn't even graph the tangent of x yet. But pretty much tangent of x would look like this. And normally for tangent of x it would go negative. But anyways, when you take the absolute value, it'll be above. It'll be above like that. And so this will be absolute value of tan x, absolute value of tan x. And by the way, absolute value of sine x. And so you can see, if we use the absolute values, absolute value of tan x will always be above absolute value of x, right, on both sides. And absolute value of sine x will always be below sine x. And remember, when we're looking at that, we're focused on the point that we're taking the limit at. And so that's the reason why it works. So we can now see why we have to put absolute values there. And so yeah, that's basically it. Now we're ready to bring sine of x over x into the picture, which we haven't even done yet. That's fine. We can do that now. Notice how if we were to divide sine x, or if we were to divide absolute value of sine x, this middle term right here, it's going to have x over sine x, which brings this idea into the picture, right? It's just a fraction of x and sine x, basically. All right, and this right here, it's always going to be 1, so we get 1 is less than or equal to, right? And this right here, it's going to become the absolute value of x over the sine of x, right? And this, when we do tangent of x divided by the sine of x, it turns out that's going to become 1 over the cosine of x. So that's what we get. So this is x over the sine of x. We need sine of x over x. And so to do that, we just have to take the reciprocal of this. So pretty much it flips the numerator and denominator. And so when we do that, we get sine of x over x. And right here, the reciprocal of 1 is just 1. And right here, the reciprocal of 1 over the cosine of x is just the cosine of x. Now it turns out that when you take the reciprocal and using inequalities, the inequalities are actually going to change sign. Right? It changes sign, interestingly enough. But why? Why would that happen? This is actually a much more simpler solution. For example, if you have just 2, 3, and 4, we know that this is true. 2 is less than or equal to 3 is less than or equal to 4. If you take the reciprocal, 1/2, 1/3, 1/4, it makes sense that you have to put greater than or equal to there instead of less than or equal to. And so you can see how that works as well, right? So as you can see, that's why we flip the sign when we take the reciprocal. Okay, so now, what do? By the way, I forgot to put absolute value there. But do we even need the absolute value sign anymore? Do we need that? It turns out, well, one, remember, absolute value, the whole point of absolute value is to take a negative number and make it positive. But around the vicinity of x approaching 0, 1 is always positive, and the absolute value of cosine x, well, cosine of x without the absolute value is always positive around x equals 0. So we don't need the absolute value sign if 1 is already positive and cosine of x is already positive. Because if we already know for the cosine of x, around the vicinity of x equals 0, this is what the cosine of x looks like, right? Not absolute value, just regular cosine of x. Cosine of x is positive. In fact, it equals 1, interestingly enough. But yeah, obviously. But anyways, the cosine of x is always positive around the vicinity of x equals 0. So we don't need these absolute value signs anymore. We can get rid of them. That is definitely a good thing, right? Because, yeah, that'll pretty much be it. And so this is what we actually are doing. We have now gotten sine x over x, and we've been using the squeeze theorem to evaluate it. Now we can take the limit as x approaches 0 of all of this stuff. And to make this simple, I don't think this is really valid, a way of showing it, but I'm just going to do this. This is probably not a valid way of taking a limit. You probably have to say, oh, limit of this is greater than or equal to the limit of this, is greater than or equal to the limit of this. You probably have to write it like that. But this is obviously, it makes sense. Anyways, limit as x approaches 0 of 1 is just going to be 1. All right, again, we don't know this limit. And the limit as x approaches 0 of the cosine of x is just the cosine of 0, which is 1. There it is. And so based on the squeeze theorem, we can now conclude that the limit as x approaches 0 of the sine of x over x is equal to 1. There it is. So now we can see that this right here is where it comes from. It's just all this weird geometry and this using the squeeze theorem for it. Who even does that, right? It's crazy. It's cool. And so yeah, this idea of the limit as x approaches 0 of sine x over x is used to derive the derivatives of sine x and cosine x. It's super important. And for some reason, when you're in your calculus classes, they'll just ask you, no, using this limit, find another limit. It's just really weird. They'll do stuff like that too. But that's pretty much it. That's the limit as x approaches 0 of sine x over x.